Welcome, Android developers. I'm excited to introduce you to today's topic, Mastering Kotlin Coroutines for Android Development. This presentation will help you understand how coroutines work, share best practices, and delve into some advanced error handling techniques. We'll see how coroutines can make your asynchronous programming easier and your apps more responsive and efficient. So let's get started. So what exactly is a coroutine in Kotlin? Well, think of a coroutine as a lightweight thread that helps us write asynchronous code more easily. It allows us to perform tasks without blocking the main thread, which is crucial for keeping our apps responsive. Essentially, Kotlin coroutines make it simple to handle background operations like making network calls, accessing a database, or running long computations. They do this by suspending their execution when needed, but without actually blocking the thread they're running on. This way, we can write code that looks sequential and straightforward, yet runs efficiently in the background. This concept ties into our overall goal of creating smooth, responsive applications that manage complex tasks seamlessly. All right, let's talk about launching coroutines in Android. On this slide, you see an example, lifecycle scope. Launch, val result equals fetch data, text view text equals result. What this means is that we can start a coroutine tied directly to the lifecycle of our UI component, like an activity or fragment. The lifecycle scope is designed specifically for this purpose. It ensures that if the component is destroyed, say, the user navigates away, the coroutine is automatically canceled. This helps us avoid potential memory leaks and unnecessary background work. Now there's also view model scope, which is meant for view models. Coroutines launched here are canceled when the view model is cleared, keeping things clean and efficient. The key takeaway is that these scopes help us manage coroutines safely and effectively, depending on where they are used. Connecting this to our overall theme, it's all about writing robust, lifecycle-aware asynchronous code that keeps our app responsive and leak-free. Let's dive into understanding job in Kotlin coroutines. Think of a job as the manager of a coroutine's lifecycle. It acts as a handle that gives you control over the coroutine's execution. For example, with a job, you can cancel a running coroutine if needed. You can also check its current status, whether it's active, completed, or canceled. And if you need to wait for the coroutine to finish before proceeding, the job allows you to do that too. Now, a practical example helps solidify this concept. When you launch a coroutine, you often assign it to a job variable. For instance, you might write val job equals launch, do something long-running. Later, if you decide to cancel that operation, you simply call job cancel. This way, you're actively managing the coroutine, stopping it when necessary. This example highlights how obtaining a job instance during launch gives you direct control over your asynchronous tasks. It's a key part of managing coroutines effectively and ensures you can handle long-running processes gracefully within your overall application flow. Now, let's talk about the with context function, which plays a key role when we need to switch between different dispatchers within a coroutine. Think of it as a way to temporarily change the execution environment for a specific piece of code. For example, if we're doing a database operation, we can use with context dispatchers, I/O, to make sure that task runs on the I/O dispatcher, which is optimized for such operations. This way, the code inside the block, like database get data, executes on the appropriate thread without blocking the main thread. What's really important here is that with context is non-blocking. It suspends the current coroutine, meaning it pauses its work until that block completes, but it doesn't block the thread itself. This keeps our app responsive and smooth. Another key point is efficiency. By moving long-running or I/O-bound tasks, like network calls or database access, off the main thread, we prevent UI freezes. And once the block finishes with context, automatically restores the original dispatcher, ensuring our scope remains safe and predictable. So, in the big picture, with context helps us manage threading effectively, keeping our app responsive while performing necessary background operations. Let's take a closer look at the main coroutine builders: launch, async, and run blocking. Starting with launch, this is what I call a fire and forget builder. It launches a new coroutine without expecting any result back. It's ideal for operations where you don't need to return anything to the caller, like updating the UI or logging information. Next, we have a sync. This one is used when you want to perform concurrent operations and get results from them. It launches a coroutine that returns a deferred object, which you can await later to get the result. Think of it as a way to fetch multiple data sources at the same time, improving efficiency. Finally, there's run blocking. This one blocks the current thread until the coroutine inside it completes. It's mainly used in testing or in main functions where blocking is acceptable. Basically, when you need to bridge between blocking and non-blocking code. Understanding these builders helps us choose the right tool depending on whether we want to run something asynchronously without waiting, with waiting, or synchronously blocking the current thread. Structured concurrency is a core principle in Kotlin coroutines that helps us manage coroutines more effectively. Essentially, it means launching new coroutines within a specific coroutine scope, which acts like a container for related tasks. This setup brings several key benefits. First, there's automatic cancellation. When we cancel a parent scope, all the child coroutines running inside it are also canceled automatically, which is great for preventing resource leaks. Next, error propagation is simplified. If an exception occurs in a child coroutine, it gets passed up to the parent. This makes centralized error handling much easier. Lastly, structured concurrency creates a clear hierarchy, making it much easier to understand and reason about the lifecycle and dependencies of our coroutines. For example, in this code snippet, if we cancel the coroutine scope, both task 1 and task 2 are canceled too. So overall, structured concurrency helps us keep our asynchronous code predictable, safe, and easier to maintain as part of the broader coroutine management strategy. Let's take a closer look at understanding coroutine dispatchers. Dispatchers are really the core of managing how and where our coroutines run. They determine which thread or thread pool a coroutine executes on, and this is crucial for managing concurrency efficiently. Starting with dispatchers. Main, this one runs your coroutines on the main Android UI thread. It's essential when you need to update the user interface or interact with UI elements, because those operations must happen on the main thread to keep the app responsive and avoid ANRs, which are those frustrating, application not responding errors. Next, we have dispatchers, I/O. This dispatcher is optimized for disk or network input and output operations. Think of tasks like reading data from a database or making API calls. That's where I/O comes into play. It uses a shared pool of threads, which is perfect because blocking I/O operations can take some time, and you don't want to tie up your main thread. Then there's dispatchers, default, which is geared towards CPU-intensive work. Imagine sorting large lists or performing complex calculations. That's where this dispatcher shines. It also uses a shared thread pool, but the number of threads is limited to the number of CPU cores available, helping to optimize performance without overloading the system. Finally, we have dispatchers, unconfined. This one starts executing in the current thread, but after a suspension point, it can resume in any thread. Because of its unpredictable threading behavior, it's generally not recommended for everyday use. It's mainly reserved for specific advanced scenarios where you need that kind of flexibility. Understanding these different dispatchers helps us assign the right tasks to the right threads, making our apps more efficient and responsive. It's a key part of managing concurrency effectively in Kotlin coroutines. Handling exceptions in coroutines is a key aspect of writing robust asynchronous code. When an unhandled exception occurs in a coroutine, it cancels its entire scope and propagates up to its parent. This means that if we're not careful, a single error can cause a cascade of cancellations, affecting multiple concurrent tasks. That's why proper exception handling is so crucial. One common method is using try-catch blocks. This is familiar territory for most developers. Wrapping your suspending functions inside a try-catch allows you to catch and handle errors gracefully, preventing the entire scope from crashing unexpectedly. Another important tool is the coroutine exception handler. Think of it as a global error handler you can attach to your coroutine context. It catches uncaught exceptions that escape your try-catch blocks, which is especially useful for logging errors or showing a friendly error message to users. Finally, there's supervisor scope. This is a special kind of scope where if one child coroutine fails, it doesn't affect its siblings. This is particularly useful when you have multiple independent tasks running concurrently, and you want to ensure that one failure doesn't cancel all the others. It helps in building resilient applications where individual failures are contained and managed effectively. Connecting all these points, the core idea is to handle exceptions thoughtfully so your app remains responsive and stable, even when things go wrong. Proper exception management in coroutines is essential for creating reliable, user-friendly applications. Let's talk about safe cancellation and timeout handling in coroutines. First, safe cancellation relies on cooperative cancellation, which means that coroutines need to actively check for cancellation requests. For example, in a suspend function like doWork, you should regularly check the isActive property within your work loop. This property allows the coroutine to determine whether it should keep running or stop gracefully. To cancel a coroutine, you simply call cancel on its job instance, which sends a cancellation request. Now, when it comes to operations that must finish within a specific time frame, we use timeout. This function enforces a maximum duration for a block of code. For instance, with timeout, 5000 wraps a network fetch, ensuring it doesn't run longer than 5 seconds. If the operation exceeds this limit, a timeout cancellation exception is thrown, giving us a chance to handle the timeout scenario properly. The best practice here is to always wrap with timeout in a try-catch block. This way, you can catch the exception and respond gracefully, like informing the user or retrying the operation. Overall, these techniques, checking isActive, canceling jobs, and using with timeout, are crucial for writing responsive, well-behaved coroutine code that can cancel or timeout operations safely and effectively. Thanks, I really appreciate your time and attention today. I hope the key points we discussed have given you some valuable insights to take away. Remember, whether it's about the strategies, the data, or the overall approach, each element plays a crucial role in achieving our goals. Your engagement and questions are what make these discussions meaningful. So, thank you again for being here and for your commitment to continuous improvement. I look forward to working with you all as we move forward.